Hey everyone, Mr. Hauk here. In this video, we're going to be looking at the 8.2 notes on complex numbers. All right, so let's go through this. We're actually going to go through mathematics, quick little exploration activity, and then we'll get into the quick notes and check your understanding. So, in elementary school, you learned how to graph real numbers on a number line. Later on, when you're middle schoolish, you started learning how to graph on the rectangular coordinate system, x's and y's. And now we're going to be graphing complex numbers, okay? And complex numbers have two parts. They have a real component and they have an imaginary component. So let's talk about how to actually graph these things. All right, so here's an example of a complex number, 3 plus 2y. The real component is 3. The imaginary component is the component with the I. Okay, so the imaginary component is 2. Now, in the complex plane, and we can see it right here, we have the real axis, which is taking the place of the x-axis, and we have the imaginary axis, which is taking the place of the y-axis. So if I wanted to plot the point, the complex number 3 plus 2y, since the real part is 3, we would go 1, 2, 3 on the real axis. And since the imaginary component is 2, then we would go 1, 2 on the imaginary axis. So this right here would be our point 3 plus 2y. All right, as a coordinate, we would say 3, 2. So as a coordinate on this graph, we'd say 3, 2, 3 in the real direction, 2 in the imaginary direction. Okay. Next, we want to look at the coordinates of this complex number in polar coordinates. So we learned previously how we can convert from polar to rectangular rectangular to polar coordinates. So we know that we need to find r and theta. So r is going to be plus or minus the square root of first component squared plus the second component squared, 3 squared plus 2 squared. Because remember, this is giving us the distance from the origin, okay? We're finding the distance from the origin right here. So we're still doing horizontal component squared plus vertical component squared. We're taking the square root. It's just like Pythagorean's theorem, okay? So plus minus, that's going to be 9 plus 4. All right, so root 13. Root 13 is going to be our r value. Remember that we take the positive r value. For the angle, tangent of theta, we know that the angle in radians is going to be, the tangent of theta is going to be the y value divided by the x value. So in this case, 2 divided by 3. And since this is, obviously, if you look on your unit circle, there's no angles with a tangent value of 2/3. So this is an example where we would go ahead and use a calculator. We would have theta equal the inverse tangent of 2/3. Okay, let's go ahead and throw this into a calculator. I'm going to open up Desmos on a separate screen. And let's go ahead and plug that in. Getting 0.588 is what I'm getting. Now, if you remember when we were looking at polar coordinates and we were converting polar coordinates from polar to rectangular and rectangular to polar, we talked about how we have to be careful about the quadrant that we fall in. Notice that this point is falling in quadrant 1. You have a positive x, positive y, or in this case, positive real, positive imaginary. So it's falling in quadrant 1. Remember that when it falls in quadrant 1, we do not need to adjust the angle that a calculator would give us. So that is going to be our angle, 0.588 radians, which means In polar coordinates, we have root 13, comma 0.588. Okay, following from exactly what we did previously with polar and rectangular coordinates. So number 4, a complex number can be represented using the point 4 comma 5 pi over 6 in polar coordinates. So this is our r, this is our theta. Graph the point on the complex plane above. Okay, so I'll do this one in purple, I guess. So 4 is our r, 5 pi over 6. So 1, 2, 3 to the 4th circle. We're going to 5 pi over 6, which is right here. This would be 2 pi over 3, 3 pi over 4, 5 pi over 6. So we are right here at this point. So this is our 4 comma 5 pi over 6 in polar coordinates. All right, what is the real component? Okay, so from yesterday, so if we look here, if we're looking at our imaginary axis and our real axis, we're looking at this graphing system. The real component is coming from the x coordinate. Okay, we saw from yesterday the x coordinate is x equals r times the cosine of theta. Here our r is 4 times the cosine of 5 pi over 6. There's our theta. That's going to be 4 times negative square root of 3 over 2. Here's like a 4 over 1, so the 4 and the 2 reduce. We're going to get negative 2 root 3. Blue. All right, so there's our real component. Again, the real component is coming from the x value because the real axis is taking place of the x-axis here. The imaginary component is going to come from the y value. In this case, we can already see it's 2, but let's go ahead and show that it's 2. So we know that the y value, and again, in this case, the imaginary axis is taking the place of the y-axis. We know that the y value came from y equals r times the sine of theta. So this is going to be equal 4 times the sine of 5 pi over 6. Sine of 5 pi over 6 is 1/2. 4 times a half is 2. Okay. So our real component, negative 2 root 3. This is coming from x equals r cosine theta, because again, the real axis taking up the x-axis. Imaginary component is coming from the y coordinate, r times sine theta. Now, if I wanted to write this, take these, the real and the imaginary component, and write it as a complex number, a plus bi, well, again, we have the real first, the imaginary coming next. Real component plus the imaginary component times I. So this would be real component, negative 2 root 3, plus imaginary component 2 times I. Right. Part 5, just like the size or magnitude of a number is its absolute value, or the distance from 0, the magnitude of a complex number is its distance from the origin in the complex plane. What is the magnitude of the complex number 1 minus 4i? So one way that we can think about this is we can take our complex number and we can write it as if it was a rectangular coordinate. So as a rectangular coordinate, the real part is like the x value. The imaginary part, minus 4, or negative 4, is like the y value. So if I was going to go and plot this, 1 minus 4i would look like the coordinate 1 comma negative 4. It'd be right here. This would be 1 minus 4i. Okay? Now, taking that as an x and a y, we can go ahead and find the magnitude of the complex number would be the same thing as finding the r value, the distance from the origin. So we can go ahead and say square root 1 squared plus negative 4 squared, which should equal square root 1 plus 16, or root 17. Okay, so this complex number, 1 minus 4i, which can be represented as the rectangular coordinate 1, negative 4, when we're graphing on the complex plane, would be square root of 17 away from the origin. Or another way for us to represent this is we could say the magnitude of 1 minus 4i is root 17. Okay, these little bars right here, these mean magnitude. All right. So let's go ahead, jump to the quick notes. Let's write down, let's kind of formalize this a little bit. All right, so first thing, a complex number, and we're going to use lowercase z to represent a complex number. A complex number z has a real and an imaginary component. All right, a complex number z has a real and an imaginary component and can be graphed on the complex plane. Okay, and on the complex plane, it's very simple. The x-axis is the real axis. The y-axis is the imaginary axis. Okay. Second, if coordinates for the point, so if coordinates for the complex point are given in rectangular form, coordinates for the complex point are given in rectangular form, like this, a comma b, then your complex number z will equal a plus bi, where here the x value is representing the real part, the y value is representing the imaginary part. Okay, so that's if your coordinates for the complex point are given in rectangular form. Let's say the coordinates, if your coordinates are given in polar form, r comma theta, then we have a different way to represent the complex number z. Then your complex number z is going to be represented as r times cosine of theta. Remember, this is r times cosine of theta is x plus I times r sine of theta. Remember that r sine of theta is representing y. So x plus y times I. Same deal here. Notice that, in the rectangular coordinates, x, the real part, plus the imaginary part was represented as y. Same deal is happening here. Real part, x, r times cosine theta, plus imaginary part, y, and the imaginary part, the y coordinate, multiplying to I. Okay? Or alternatively, notice that we have an r in common right here. You could also write your complex number z with the r factored out, cosine theta plus I times sine theta. Okay, so you'll see it like that occasionally. Both are fine, both are equivalent. All right, so let's try some check your understanding problems. Number 1, a complex number w is graphed below, so we see it right here. Write w in rectangular form. So rectangular form means we're writing it like this, okay? A plus bi. So this is the point. It looks like the point -6, comma -3. All right, so -6 is the real part, -3 is the imaginary part. So our complex number w is going to be -6 minus 3i. Real part plus imaginary part times I. Real part, imaginary part. All right, now let's represent w. Let's write w in polar form. In polar form, to be able to write it in polar form, we need r and we need theta. Okay, so r equals plus minus square root the x value, so written as a point, the x value squared, -6 squared, plus the y value squared, -3 squared. So this is going to be 36 plus 9, which is root 45. Root 40, not root 49, sorry, root 45. And 45, 9 times 5, so this is the same thing as 3 root 5. Okay, the theta, so tangent of theta equals the y value divided by the x value, -3 divided by -6, which is 1/2. And none of our tangent values from the unit circle are equal to 1/2. So we need to go ahead and say theta equals the inverse tangent of 1/2. I'm going to jump over to Desmos on a separate screen. Let's go ahead and calculate this. So inverse tangent of 1/2. I'm getting 0.464. But remember, anytime we're getting theta, we have to be aware of where our point is. We can see the points in the third quadrant. We can also look at our point written as an xy pair. We can obviously tell it's in the third quadrant because the x is negative, the y is negative. But if you remember from the previous set of notes, if the calculator gives us an angle, but we know that the point is supposed to be in the third quadrant, we need to compensate, we need to adjust the angle by adding pi. Okay, so if you remember from that set of notes, the 8.1 notes, whatever angle the calculator gives us, if the point's supposed to be in quadrant 1, we don't need to make any adjustments. If the point as a xy pair is supposed to be in quadrant 2 or 3, we add pi to it. If the point is supposed to be in quadrant 4, we add 2 pi to it. So since this point is in quadrant 3, whatever angle the calculator gives us, we add pi to it. So go ahead and add pi to it, plus pi, and we get 3.605. Okay, so our r value, remember we're taking the positive r value, you can either say 3 root 5 or you can say root 45. So our complex number in polar form, according to what we have right here, our complex number in polar form is going to be r on the outside, in our case that's 3 root 5, times cosine of the angle. Cosine of our angle is 3.605 radians. So cosine 3.605 plus I sine 3.605. so here's our complex number W written in polar form. Okay. Number 2, a complex number is represented in polar coordinates 5, 2.3. Find its real and its imaginary component. All right. So just like previously, polar to rectangular, x, which is representing the real, I can spell, there we go, x, which is representing the real, because again, as a rectangular coordinate, x value represents the real, the y value represents the imaginary. So x, which is representing the real component, is r times cosine of theta, which is 5 times cosine of 2 pi over 3. Cosine of 2 pi over 3 is negative a half, so this is 5 times negative a half, which is negative 5 halves. We know that y value, which is representing the imaginary component, is r times sine of theta, which is 5 times the sine of 2 pi over 3. Sine of 2 pi over 3 is root 3 over 2, so 5 times root 3 over 2, which is just simply 5 root 3 over 2. So our real part, negative 5 halves. Our imaginary part, 5 root 3 over 2. Okay? And if I wanted to write it as a, in rectangular form, the complex number as a rectangular form, I would say negative 5 halves plus 5 root 3 over 2i. Okay, but we were just asked to find the individual components. All right, number 3, write the complex number in standard rectangular form. So they gave us the complex number in polar form. This 8 is representing our r, and pi over 2 is representing our theta. These are actually pretty simple. All we actually have to do is go ahead and calculate these parts right here, the cosine pi over 2, the sine of pi over 2. So we have 8. Cosine of pi over 2 is 0, plus I times sine of pi over 2 is 1. And then we're going to take our 8 hanging out on the outside here, and we're going to distribute it. 8 times 0 plus 8 times I. Well, 8 times 0 is 0. So you can either write it like this. You can say 0 plus 8i to kind of show you that the real part is 0, the imaginary part is 8. Or obviously we don't need to put the 0 there. We can just write 8i. But even if we just write it like this, we still need to recognize, if we just write it like this, that the real part is 0, the imaginary part is 8. Okay? And then finally, number 4, write the number 4 minus 4i in polar form. So we want to write it in polar form. We need r and theta. Remember that, this is in rectangular form. As a point, this would be 4, negative 4, as like an xy coordinate pair. If we're going to plot it on the polar plane, it'd be the point 4, negative 4. So in polar form, our r plus minus square root 4 squared plus negative 4 squared. This is going to be plus minus square root 16 plus 16. Right, which is 32. Square root of 32, since 32 is 16 times 2, that'd be 4 root 2 if we simplified it. And then our theta, tangent of theta, equals the y value, or as an xy coordinate pair, this would be negative 4 for the y over positive 4, which equals negative 1. We do have tangent values from the unit circle that equal negative 1, and again, anytime you're finding your angle theta, you need to be aware of what quadrant you're in. So here, the point 4, negative 4 would be in quadrant 4. Okay, so we need to know what angle in quadrant 4 gives us a tangent value of negative 1, and that would be 7 pi over 4. Okay, so in polar form, our number would be, let's just call it z, would be 4 root 2, parentheses, cosine 7 pi over 4, plus I sine 7 pi over 4. All right, so go ahead and try the homework for 8.2. I believe I already have my homework key posted on eClass. So yeah, try out the homework, check with my homework key, and let me know if you have any questions when I return. Bye, y'all. Have a great